Okay, so good morning and welcome back. So this week, first lecture, so Vikram is going to give the first one. So he really needs no introduction. I mean, he born and brought up here. So then he went to Cambridge and for bachelor's, and then to Princeton, and he worked with Camilo. Yeah, without further delay, I'll request Vikram to continue.
Thanks so much for coming and thanks for having me here. So the goal of my lectures will be to continue where Hyunju left off. So it will be to give more details about the proof of the L3 strong on Saga conjecture. But before that, I guess now a small tradition has developed of trying to give some exercises. So let me start with a couple of them. So I guess the first one, I guess you can say this is intermittent. Intermittent Mikado flows in 1D or in 2D, I suppose. Can everyone read this? Yeah. Start with the half. Start from here. I see. Okay. Good. Is it too small? Yes. Okay. Good. Okay. So let me try to write bigger. So firstly, show. Let's. So let me give two parameters. So let 0 less than or less than 1 and lambda be something quite large, right? So show there exists lambda r periodic function, so lambda r inverse function, let's call it psi from R to R, right? Such that the support of psi in a period is contained in is of size, it's contained in an interval of size lambda r. So let's say minus lambda, sorry, lambda. So the picture is this. So you have, say, 0, and you have some interval which is of size lambda r inverse. And the function I want it to be supported in something just of size lambda inverse. So it's some function supported here, it's 0 here, but now it's periodic, right? So this is, okay, I guess there exist such functions, but moreover, which satisfy the following properties. So in L2, psi is normalized to 1. And then for any p, the LP norm, so I guess for any p between like between 1 and infinity, inclusive, psi in LP will be bounded from above and below by constants which are universal. I mean, constant depending on p, let's say, of this r to the power over p minus 1 over 2. And I guess that's all. No. Then if I take, so let's call this direction x. So this direction is x. If I take yeah, so let's say, so this, and also the mean is 0. mean of psi is 0. Now if I take dx inverse, so basically integrating in x, this guy is again going to be a lambda r periodic function, which is supported in this. So this is again lambda r inverse periodic with same support. And moreover, if you this thing say in L2, let's say L, yeah, let's just do L2. This thing gains this guy, the support, so it's like 1 over lambda. But if you now do the same thing with dt inverse of psi square minus 1, so this again has mean 0 because it's been normalized in L2 to be 1. So this one again will be a lambda r periodic function. So you can try this. So this one, if I measure it in say L2, this one will only gain 1 over lambda r. And so the point of this exercise is to show that such a function psi exists. And another thing which you can do is to show that none of these bounds can kind of be improved. So especially the one which is important, I guess, for these lectures is this guy. So this guy can't be improved to any other things. You can't get 1 over lambda here. Sorry, t is an x. Thank you. All right, and okay, so we are not yet in 2D. So now let's go to 2D. So let's call this x, and let's call this direction say y. Now show that if I call w x and y to just be psi of x, and then so it just depends on the x variable, and it's just the vector in the y direction. So it's a vector field that only points in this direction. Then this is a stationary pressureless solution to incompressible Euler, which means basically here is that divergence of W is 0 and W dot grad W. So stationary just means the dt term is not there. It doesn't depend on time. This is the advective derivative, and pressureless just means there's no pressure. So this is 0. And so these are the type of building blocks we'll use, but ours will be in 3 dimensions and not 2 dimensions like this one. Okay, and the second exercise is something Laszlo suggested, is going to be this LP decoupling, but in a very simplified setting. So again, let lambda and capital lambda be real numbers, such that lambda is less than, let's say, maybe just to be safe, I'll add 1 over 2. I think this should work. Then, and given 2 functions, given f and psi, such that psi is lambda inverse periodic, and F satisfies that if I take any number of derivatives. So F and psi are, sorry, I should have written, they are functions from R to R. And F satisfies if I take derivative in X to the nth power. Say if I measure it in L infinity, this is going to be less than or equal to some constant depending on n, and this little lambda to the power n. Right. Let's say this for all n. Then you actually have an improved Holder inequality. So you can actually measure the L1 norm of F psi. You can estimate this by the L1 norm of F and the L1 norm of psi. So generally there would be a P and Q, with P and Q being conjugate exponents, so like 2 and 2, for instance. But if you have these properties that F and psi like decouple in frequencies, in the sense that F is very slow compared to psi. So here what that's being codified by the fact that all the derivatives of F are this going as lambda to the n, and this little lambda is much smaller than the big lambda. Right? And the psi is something which lives at the much higher frequency of capital lambda. And so if you have a product of two functions like this, where you have this one being the slow function in this setting, where it just depends, where slow is in the sense that the derivative cost is just a little lambda, which is much smaller than the big lambda. So in that sense, this is relatively slower to psi. And so this we'll call the slow variable or the slow function, and this we'll call the fast function. Then these actually decouple. So you can have an L1 and L1 bound. So these are the two exercises, and are there any questions? Or do you guys have any questions regarding this? It probably can be any R less than 1. At least the way I've stated it, yeah. I have not actually written the problem precisely and solved it. So I hope this is correct. If it's not correct, then feel free to replace this by some other number, which is smaller than 1, but not 0. Sorry? The ratio should be less than a constant, which is between 0 and 1. I think that's correct. Which will affect this constant. Yes. Okay. So maybe I should call this C. C. And this constant here will be affected by this ratio. Thank you. Cool. All right. So let's start. So we'll start with a review of what Hyunju said. So review. Okay, so we are interested in the incompressible Euler equations in 3D, which satisfy the local energy inequality. So we'll have T comma X belonging to R cross the 3-dimensional torus, and we are looking for a solution to the relaxed equations. So U, so let's say, let me just call it U. You need a velocity field, a pressure, then you need a Reynolds stress, and you need this current, which comes from the relaxation of the local energy inequality. And these satisfy the following. So the divergence of U is 0. Then you have the relaxed momentum equation. And then you have the relaxed one, divergence of R. And then you have the relaxed local energy inequality. So you have the trace of R here being advected. Then you have this term, and then you have the term involving psi. Right, so this is the system where we want to iterate on. Right. And I guess what Hyunju concluded with is, in order to iterate this, in order to find the W, so you want to say UQ plus 1 equals UQ plus some perturbation WQ plus 1. In order to get the right estimates, which I won't write down here right now, but it's what Hyunju wrote, there is a tension between the quadratic terms and the cubic terms. And kind of what that forces is that this RQ that she wrote, so the intermittency parameter RQ, which is basically the same as the intermittency parameter R in that question, here will always essentially have to be this lambda q over lambda q plus n bar to the 1/2. So this is what she showed in the heuristics. Sorry? This one? This one? Well, okay, now I don't remember if Hyunju used the hat notation here or not. I don't know what's in your notes, actually. I'm sorry. Thank you. Yes, thank you. Right. So this is what she showed, and she showed that if this power a half, I mean, if it was larger than a half, then you won't be able to close something in L infinity. The intermittency is too much. That means the L infinity norm is too large. And so you can't close something in L infinity. And if it's too small, then there is this issue between the quadratic and cubic terms. So really, this is the only amount which kind of works. And so the picture is as follows. And so this is again what Hyunju drew. So this axis denotes frequency. And so our error is something which is at frequency lambda q. So here is where our errors lie. So RQ and phi q, they lie here. And the way we are going to correct it is we are going to correct it with some WQ plus 1. And this one will have highest, I mean, it's highest frequency at lambda q plus n. Right? But because we have this intermittency parameter, again, just from the toy model, in our intermittent Mikados, we'll have the highest derivative cost being this guy, lambda q plus n bar, but these will be periodized with periodicity given by lambda r. So the periodicity will be reflected here. So the periodicity will be lambda q plus n bar times rq, right? Which, if you just do a quick calculation, is just the geometric mean of lambda q and lambda q plus n bar. Right? Okay, so this is where W lives, so it's at frequency lambda q plus n bar. But now, if you consider this W tensor W, so WQ plus 1 tensor WQ plus 1, right? We saw in what Hyunju did, there's a low frequency part which comes just from the mean of the building block with itself. And so those just have low frequencies less than lambda q. And then there's the high frequency part of this, and the high frequency part basically, so let me call this high. This is basically going to be the sum of a square, something which depends on r and phi, and it's going to be the projection of the mean. So this is just notation to say a function minus the mean of the function of W tensor W. These are the building blocks, right? And this guy, again, just from this exercise, I mean, essentially you see that it will have frequencies which are supported all the way from here to here. So the frequency support of this guy is going to be all the way from here to here. Right? And so what this forces us is we can't really think of our RQ and phi q as in each step of the iteration just as living at one frequency. So this was the case in the previous convex integration schemes and in the scheme that Camilo will talk about. It's not that you have lambda q and then you move everything to lambda q plus 1 and then solve it there and then move everything there. You really have a whole range of frequencies you need to deal with. And in order to do that, we need to do this fine chopping of this guy. So we have lambda q, then we consider lambda q plus 1, and then so on. So we need to really chop this guy up into its corresponding pieces and then try to correct each one individually. All right, and here is where something interesting happens. So now in order to, so say we have corrected lambda q, say we have corrected the errors at lambda q, which we call rqqq and phi qq in the notation that Hyunju introduced, right? Okay, so we did this with some perturbation which produced errors all the way here. Now we need to correct this guy, right? And this guy, again, by using the same logic, we can only use something with highest frequency lambda q plus n bar plus 1, because anything higher, and then you won't be able to close the L infinity norms. And again, by this restriction, you will need to choose the intermittency parameter to be basically rq plus 1, which will be lambda q plus 1 over lambda q plus n bar plus 1 to the 1/2. So that means that the periodicity is forced to be here. And so now you'll get kind of the new errors, which will be around here. And now you repeat. So, and now in the next step, you have lambda q plus 2, and you want to correct this, and then this will generate errors here, and then so on and so forth. So this is the type of scheme we want to implement. And you see that all of the perturbations W that we generate, they will have a lot of frequency overlap. So in the sense that the errors they produce, they will have a lot of frequency overlap. And there are difficulties in trying to implement this. And this is what I want to talk about in this lecture. So the plan of this lecture will be to try to implement this and try to note all the main difficulties. And the subsequent lectures will be about how we deal with these difficulties. All right. So any questions? Yeah, this process will continue up to n bar steps, but now then you've introduced more errors at higher things. So actually it just keeps continuing on. And as q goes to infinity, you get a solution of incompressible Euler. And the hope is that the RQs will go to 0 in L3/2, and the phi will go to 0 in L1. So actually, like in the end, if you test with some test function and do an integration by parts, you see that these go to 0 as distributions. And so you actually get a weak solution of Euler which satisfies this local energy inequality. Actually, maybe I should have written the inequality here. Yeah. Yeah, no, so you can try to do that, but that gives you some terms which a priori don't go to 0 as distributions, and it's kind of hard to deal with. Yeah, so this is a good point. So usually the way you derive this equation, say without the relaxation, is you take the momentum equation, take the dot product of that with u, and then just by some algebra, you get this equation. So provided everything is smooth and you can do all the usual calculus. Now, everything here is smooth in the relaxed equation, so you could try to do the same thing. You could dot product this with u, and then try to get something here. But what you would get is you'd have divergence r dot u, and this you can write as divergence ru. But then you'd have another term which I think is nabla u. So this means you take nabla u, this is a 2x2 matrix, R is a 2x2 matrix, you multiply them together and take the trace. So you'll have this term, and this term doesn't go to 0 as distributions. And it's kind of, yeah, we don't know of a way of like trying to massage this. So the way we actually get this, and I don't think Hyunju talked about it, or maybe she did. So the way we derive this is to say we had an exact solution of Euler. So this is what physicists do all the time. and then you just cut it off at some frequency. So you do a mollification at some length scale. And when you do that, the mollification or the frequency cutoff will commute with all these derivatives, but they will not commute with the nonlinearities. So here you see that the commutator between the quadratic nonlinearity and taking the projection is what gives rise to R, and this is why this R has divergence form as well. And similarly here, and here you see that it is the cubic term. So if you take u square over 2, and you then mollify that at some length scale, versus if you take u modified at that length scale and ul square over 2, that is precisely this cubic order term which goes into phi. So that's how this equation is derived. It's not through the usual standard energy method. Yeah. Yeah. Thanks. Any other questions? All right. Okay. So let's try to implement this and see where we get and what we need. All right. So okay, over here, how far can I write up to? Is this okay, or do I need to cut it at half? Half. All right. Yeah. So in order to do this, let's first talk about the Reynolds transport error. Right. So this is this error term which is of the form you have divergence inverse, and then you have dt plus uq dot nabla of wq plus 1. Right, and we want to estimate this. Okay, so let's write this down. So let's expand just the principal part of this. So we have divergence inverse of this material derivative. So this one I'll now start calling dtq. So this is dtq of wq plus 1, and wq plus 1 is just the sum. At least the principal part will just be this coefficient A, which depends on R and psi, and then this Mikado flow, so W, which is something with highest frequency lambda q plus 1, and then it has intermittency RQ. Okay, so here what we want is, we want at the end this estimate, right? We want to gain a lambda q plus n bar from taking the divergence inverse. And we only want to lose a derivative on the low frequency. So what that means is that I don't want this material derivative to hit this fast oscillating function. Because if it did that, then a naive estimate would be that this costs lambda q plus 1, lambda q plus n bar, sorry. Right, because that's the highest frequency of this. Right, and so this will throw out this, and which will exactly cancel kind of the gain which I'd hoped to get, which is lambda q plus n bar. And so then, I mean, this estimate, I mean, it doesn't get much smaller. And Hyunju showed that you need to gain this in order to close. And so the first thing is I want this thing to only hit this guy. So I want this to equal divergence inverse of dtq psi q phi q, and then you have this. Right? Okay, and in order to do this, I mean, we'll have to figure out a way in which to essentially get something like this. I don't know if this has already been covered by Camilo, or I mean, it's been mentioned many times. But the idea will be we'll not have just the Mikado flow, but we'll have the Mikado flow being transported by the Lagrangian flow associated to UQ. So that's what we'll need. Okay, and then secondly, okay, so we're going to measure this guy because this is a Because this is Reynolds error, this we'll measure in L3/2. Right, so let me replace all of these by less than equals. Right. And now we want to use the fact that these two guys again decouple in LP. So this is the slow variable, or this is the slow function, and this is the fast function. And so we want some decoupling. So we'll need something there. But sorry, one more thing. And we want this divergence to gain this. So we want, if we assume that the divergence gains the 1 over lambda q plus n bar, then we want these to decouple. So then we want this W 3/2. Right? And so what we need now is an estimate of dtq, or of the material derivative of these errors, rq and phi q. So that's another thing we'll need. And the estimate that Hyunju wrote for this was that this costs lambda q delta q to the 1/2 rq minus n bar to the 1/3. So that's the estimate of this guy. Then, sorry, that's the material derivative cost. The estimate of this guy will have a delta q plus n bar to the 1/2 coming from the size of this guy, right? Because rq had size delta q plus n bar, and a is supposed to be such that a square is like rq. Okay, and now you have the size of this guy measured in L3/2. So this, remember, is some intermittent function which is normalized in L2. And so, but we are going to measure it in L3/2. And so we have this, this gain of 1/3. And this we wanted to close with delta q plus 2 n bar. And this Hyunju showed was sharp with the regularity parameter beta going to 1/3. And so we need a bunch of things. We first need to be able to flow by a flow map. Now I need to go all the way back. Can I erase this? Yeah. So we need to use a flow map so that the material derivative doesn't hit the fast function. And so that's the main, so we need to first implement that. And then after that, we will need to, try to see how we get material derivative estimates on this RQ and phi Q. Okay, so we need a flow map phi. Need a flow map. Phi. Which is flowed by this equation. So dt plus uq dot nabla phi is 0 essentially. Right, so that when I compose W with the flow map, this will, so I compose this with the flow map. And so that means that this material derivative, when it hits this, will be 0 just by the chain rule. Right? But now there's a problem because UQ, remember, was everything which is not WQ plus 1. So in particular, it has all the vector fields which were added just before. So in particular, it has all of these vector fields. So the one just added immediately before, which say went from here to here, the one before that, which went from here to here, and so on. Right? And if you measure the, and now the issue is that, okay, fine, so you have all these vector fields and you need to flow by all of these vector fields. But now what happens is this flow is only defined up to the Lipschitz time scale. right? It's only there where you have good estimates on this phi. And after that time scale, you basically know nothing about phi. I mean, the estimates deteriorate exponentially. Okay, and the solution to that was to have a bunch of flow maps phi I, and each of these phi i's is defined on some interval of time, right? And so let me just briefly write that. So you'll actually have another parameter, let's say k, and here you'll have another slow variable. Let's call it maybe psi, psi k, which just depends on time. And this sum will now be over time and over k. And the purpose of this is to basically form a partition of unity. And so where this is active, you will have a particular phi k. Right. Okay, now you see the issue that this one has a time derivative in it, and this time derivative can hit this. And so when this time derivative hits this, you're basically going to see that time scale appear, the inverse of that time scale. Right, so let me write that here. So dt of the psi k will basically be bounded by nabla uq, the inverse Lipschitz norm of this. So this in L infinity. Okay. Firstly, this already is very bad. Because we are in an intermittent scheme, we only propagate L3 estimates of UQ, right? So this is what Hyunju wrote. And here we are asking for L infinity estimates. And so already this seems like, I mean, we need some idea. And this is something which I'll cover in the last lecture. So this is like, in some sense, a very technical thing, which involves splitting up your space-time domain into pieces. On each of these pieces, you have a particular estimate on nabla UQ, and then you patch them up together. But, and the upshot of that is you can really replace this with, say, the L3 norm of nabla UQ. Okay, so say you wanted to achieve this. Now, the L3 norm of nabla UQ is something you can calculate, and it's essentially going to be it's essentially going to be the derivative cos, I mean, nabla of the latest perturbation you've just added. Simply because the estimate of, let's say, WQ prime, let's say in L3, this is going to be like lambda Q prime, delta Q prime to the 1/2, RQ prime minus N bar to the negative 1/3. Right, and you'll see that simply because our solution WQ or UQ has only 1/3 different, I mean, 1/3 of a derivative, that this is going to be an increasing function of Q. So this can be a quick check as well, or an exercise, that this is an increasing function of Q prime. So UQ is just going to be composed of the sum of all of these guys, right? Because you have this as your recurrence relation, which produces the new UQ plus 1. And so when I'm actually, sorry, this should be a plus N prime. Yeah. So when I actually am estimating this for UQ, I see something quite terrible. So when the dt hits this, I'm actually going to see essentially this Q plus N bar here, which is what I did not want. And so what I want is just is exactly the UQ for which the highest derivative cost is less than this lambda Q. So yeah, so this guy is quite bad. It's in some sense all of these guys, the estimates of this. I mean, one way you can get some intuition about this is essentially very close to the current perturbation you're adding. And so the derivative cost of that, or the C1 norm of this, is basically going to be very close to this one. And so it will basically be this guy here. And this would ruin our estimate here. Because if we had that cost appearing here, then again, you'd have the problem where the lambda q plus n bar will just cancel out. And so you'll have this issue. And so you can just check that the only UQ, say, that kind of works is the UQ which is formed of all of those velocity perturbations which have highest frequency less than lambda q. And so let's give this a name. So let's call this guy UQ with a hat on top. So UQ plus 1, we wrote it here as UQ plus WQ plus 1. So let me also write this as UQ with a hat plus everything that comes kind of after. So here you'll have WQ, I think minus n bar plus 1, plus WQ minus n bar plus 1, plus dot 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 plus WQ plus WQ plus 1, which is the latest thing you added here. So you have all of these guys in between, which correspond to these velocity perturbations that you added. And the issue is that you can't have the flow map be the flow map associated to the vector field UQ, simply because this quantity here is too large for that, and this quantity here dictates what the cost of the time derivative is on the psi. Right? So this phi k, as I wrote, cannot be the flow associated to UQ, but has to be the flow associated to UQ hat. And then this is fine, but now there is another problem, right? Now we are in some sense back to the same problem, which is that this is a dt plus uq dot nabla, and now this is hitting this guy, but this is not the flow map associated to dt dot uq dot nabla. It's associated to dt dot uq hat dot nabla. And so again, you will say, okay, you've not achieved anything. I mean, there has been no improvement. You're back to square one. So the way we the way we get around this is to do the following. So we want dt plus uq dot nabla hitting this w circ phi, this to be identically 0. So let's split this up as dt plus uq hat dot nabla hitting this and the rest. And the rest would be these wq minus I, where I ranges from 0 to n bar, dot nabla of this guy. Right? This is 0, right? Just by what we discussed. This phi is chosen to be the flow map associated with this vector field, and this is the material derivative hitting it, and so this guy is 0. All right. And now we are left with this, which potentially is really bad because this is exactly the problem we wanted to avoid. We wanted to avoid a derivative landing on this fast function, on the high frequency function. And so the way we get around this is to really just impose that this guy is 0 simply by imposing that they have disjoint supports in space. So the support of wq plus 1 intersect the support of wq minus I is the empty set for I guess going from 0 to n bar. And so if we are able to make the supports of these perturbations disjoint, then we have no problem at all. This is just 0 because there's no intersection. Okay, and another way of writing this guy, and this is something we'll need to have throughout the iteration. So let's not be so specific with this q plus 1. So let me then say that this is implied by an inductive assumption of the type support of, say, WQ intersect support of WQ prime is the empty set whenever Q and Q prime are close by. I think this is right, up to plus minus 1 over here. And this is an inductive assumption that we'll need to propagate. And this is what we'll call dodging. All right. So achieving this will be the focus of the next lecture. But yeah, so once we achieve this, we indeed have that WQ minus I has no interactions with this guy here. And so it's indeed 0. Yeah, this is lower order in comparison with this. So the Nash error, maybe let me just write it quickly here. I mean, this will be relevant in what I'm going to say next. This is of the form divergence inverse. Now here you have WQ plus 1 on the outside, dot nabla UQ. Right, so here you have the derivative hitting, in some sense, the slower guy as compared to this. So there you don't have this problem, but you have some other problems, which we'll get to. Okay. Okay, so any questions about this?
There are too many ways of interaction, right? So when are you putting the next this pipe? It's not only you have to make sure they are disjoint, but also previous steps.
Yeah.
So there are something.
Yeah. So, so yeah, what Ujjwal is referring to was this fact that we saw used already, that when we compute WQ plus 1 tensor WQ plus 1, here I just wrote, so this is a sum over psi, let's say. Here I just computed the diagonal elements, right? And so they could be off diagonal elements as well, where an A psi interacts with an A psi prime. And so and the W psi interacts with the W psi prime. And these need to be 0 as well. And this is ensured by using these Mikado flows, which are these pipe flows, to have like disjoint supports in time, A in space. And a similar thing we'll need to propagate, not just for interactions of WQ plus 1 with itself, but interactions of WQ plus 1 with these previous velocity increments, all the way up to this here. From this, it's fine if we flow it, because from this, we have the correct estimate for nabla of UQ hat. That has the correct estimate. So up to here, it's fine, but all of the velocities that we added, which have their highest frequency larger than this, we'll need to impose that they have disjoint support from this guy that we're adding currently. All right, so that's dodging. And that fixes this issue that we had. The issue that this DTQ should not hit this. And this one we have solved. There's now the other issue of how do we estimate this guy, DTQ of this stress here. And so that's what I want to talk about now, is how do we get an estimate like this. And we see a similar problem again pop up. Can I erase this? And this as well. Sorry? The initial condition will be, you mean U0 and W0. So this is something, I mean, you can really choose it to be anything in some sense. No, it kind of, okay, it can be. Okay, but now I immediately erase this. Okay, I'm sorry. But one thing you can do is in this local energy inequality, so it was like less than or less than equal to something. I could have also added like a small term here, which is like E of Tx. So I can prescribe this Duchamp-Robert measure that Hyunju talked about. So I can prescribe like locally what the dissipation is going to be at any point. And for instance, if this guy is going to be non-zero, then I know that the constant function 0 will not be a solution because that won't satisfy this. So then if you start with the 0 initial condition, you'll actually be forced to form a non-trivial solution of this guy with this being the dissipation measure. So yeah, that's a good point. And I'll talk about how to do the initial step of the iteration like at the last lecture. All right.
Sorry, Vikram, I have one more question. So you're imposing some sort of this artificial periodicity.
Yeah.
Is it something related to the fact that you need this to make sure the pipes are not interacting? I suppose that you will have many options within a box that you can put your pipe.
Yeah.
And is it a surprise that the same RQ is going to work there? Like lambda Q.
I mean, it's a surprise in the sense that after talking about this, how to get the material derivative on RQ, this looks impossible.
Too many.
Yeah, I mean, this looks impossible for a very simple reason, and so we'll need to talk about that or see how we are going to get over that. But yeah, just wait maybe, I don't know, 10 minutes and then hopefully yeah. Okay. So now we need to propagate estimates on this. So we need estimates on dt plus uq Nabla of say r or phi or something like that. Let's just say rq for simplicity, but it could also be the phi or it could also be something else. Okay, now how does one get estimates of this form? So again, these will be propagated inductively, and the way one can do so is, say here you are correcting this error RQ, but you're producing all of these new errors at these higher frequencies. Now the new errors, I want to again say that they have a similar form like this. And so you want to estimate basically, so if I write it here, this is all right. So I have divergence inverse, and then I have dt q. Right? So and now this I can try to estimate just by knowing previous inductive estimates on this and the fact that this is being flowed by the flow map. Okay, so what that kind of tells me is, at least for RQ, is I have an estimate, or I can propagate an estimate inductively on this guy. Right, because this UQ hat is the one with highest frequency here, and that kind of, say, produced this error. I mean, that's a slight lie, but you have an estimate on this. But again, you have a very similar problem where you have these guys here, where you have these other guys which are being applied to RQ. And again, for similar reasons, these will not have good estimate. Actually, now that I'm saying this, I take that back. These do have a good estimate. But if you actually consider the Reynolds-Nash error, then these will not have good estimates because, again, just if you follow the same computation, but for this error, you'll see that you'll have a good estimate on WQ plus 1 dot nabla UQ hat. But now you'll have the other terms here. You'll have WQ plus 1 dot nabla of these WQ minus i's, where I again goes from 0 to n bar. And again, noting that the derivative of these w's is something which is growing in q, these will be much worse than this. And these are the ones who you can't control. And so, I mean, you'll be forced to actually again say something that these guys I want to kill. These guys I want to make 0. And so this gives rise again to some problems. So I want to implement basically the same strategy. I want to say that this is 0 because some supports are disjoint. I want to say that the support of, say, some RQ prime or RQQ prime intersect the support of some WQ double prime is empty. If this Q prime and Q double prime are kind of close to each other. I want to say something like this. Okay. But here you see a problem because all of these stresses and the current errors and everything else, they have been formed by taking a divergence inverse. And divergence inverse is a non-local operator. And so even though you have support properties of this, so we are going to see by the dodging that we're going to do a precise placement of these guys. And so this guy has support inherited from the support of this placement. When we take a divergence inverse, a priori, all of this support has disappeared. A priori, this is just some function supported on the torus, and you have no other properties about where it's localized. And this is going to be something we'll be needing. So this is something we need to implement. So we need a localized inverse divergence for this. Need a localized inverse divergence. All right. And I think I'm maybe slightly running behind on time. So let me just stop here. Or actually, no. Let me finish. Okay. So say one can do this. Okay. So say you have an operator which acts like a divergence inverse, which preserves the support. Okay. So what will that support be? So yes. So essentially, it can't be any smaller. Okay, now I'm just hand waving. Okay, let me hand wave today, and tomorrow I'll give you the precise localized inverse divergence, and then you'll see how this can be made precise. All right. So the support of this guy, at most, it can be the support of the thing on the inside. It can't be any smaller than that. Right? And so it's really dictated by the support of this here. Sorry, it's really dictated. Okay, let me just write it. So the heuristic for the localized inverse divergence will be the following. So we'll have divergence inverse of some slow function, so of something which is low frequency, times something which is high frequency. I want to say this is up to leading order, essentially, the low frequency guy times the inverse divergence of the high frequency guy. Right? So this will be the heuristic that I want to make precise with the localized inverse divergence. All right. And this is an explicit function. This is this Mikado flow that we chose and which the first exercise was based on. And this is basically like in the first exercise, this dx inverse that I wrote, like in one dimension. So I can, there's a way in order to prescribe this one. So this is also a function which I can prescribe. I can give you this function and I can tell you that this function will have some localization property. Okay, but it can't be too localized, right? Because let's consider some projection of the mean. So that has frequencies all the way between here and here. Let's consider one particular frequency here. Let's call it lambda q prime. Right? So what I'm interested in now is I have the divergence inverse hitting, I'm projecting something onto frequencies which are lambda q prime, and then I have this w tensor w. Okay. Now this w is some pipe which has, so let me just maybe attempt to draw something in 3D, right, which has this thickness given by lambda q plus n bar inverse. Right, that's the thickness of this pipe. And it's periodized to something with something such that this is lambda r. So this is lambda q plus n bar rq inverse. All right. And now when I project it to some frequency in between these two length scales here, what I'm basically getting, I mean, the best possible estimate here is I gain this, but moreover, the support of this guy can be, has to be like at least something which is contained in some pipe, which is of thickness here, given by lambda q prime inverse. Okay, this is something which I'll try to make an exercise on and make precise, but this is essentially a form of the uncertainty principle. It's saying that if I have localized to frequencies around lambda q prime, that means in space, I only know it up to a length scale which is given by lambda q prime inverse. I can't localize it more in that. So I know that the support of this has to be contained, I mean, has to contain at least this entire guy. You can't have more localization happening inside, because if you had more localization happening inside, its frequency would be given by the inverse of this length scale. But that's too high because I'm projecting it onto something here. So this is a form of the uncertainty principle, and this I'll try to make an exercise for. But basically it's saying that this guy is going to be supported in some ball of this radius around the original W, right? And so what this gives rise to, if I want this to be 0, so I want something like this, right? This guy from the discussion we just had is going to be, sorry. So I want, okay, let me step back. I want to implement this. That means for any of the new errors I make, I want this property. So the new errors I make, let me call it SQ plus 1, Q prime. And so this, for instance, is of this form. Right? It's going to be a square, whatever, RQ, phi q, and then divergence inverse of this guy, P, which is going to Q prime of W tensor W. Right? And so the support of this is going to be contained in a ball around the support of the original perturbation, which is WQ plus 1. And the radius will be given by this guy, lambda q prime inverse, right? Which is basically this. I'm taking WQ plus 1, the original thing I had. I am taking a ball of this radius lambda q prime inverse around it. And I'm saying that this is where the support of the inverse divergence lies. And this is the sharpest possible guy. You can't get anything smaller than this because of the uncertainty principle. Yeah. And so what this is basically reducing to is now I want support. Now I want not only that the supports, did I erase? Yeah. I not only want that the supports of these guys are disjoint, but I also want them to be disjoint with a certain distance between them. So I want the ball of the support of this W cube with some radius, lambda q inverse plus n bar, and then intersect with support WQ prime, a ball around this with lambda q prime inverse, this guy to be null. And so this is a stronger condition than this. It's not only saying that these two, I mean, if again, q and q prime are less than equal to n. Right. This is not only saying that these two guys are disjoint, but they're disjoint with a certain distance between them. That means if I take a ball of some radius around this guy and a ball of some radius around this guy, then they are still disjoint. And this we call effective dodging. Yeah. Here, yeah, it should be q prime plus n bar inverse. Yeah. It's basically because WQ, its highest frequency is at lambda q plus n bar, and so that's the radius that I want to think about. Yeah. So I want this, and this we call effective dodging. Okay. So these are the two things I want to implement, and we'll see that tomorrow. But immediately, let me give you, this is what Ujjwal was asking, a very simple obstruction to why this is impossible a priori. And this is because of the following. Let me erase this. Okay, so what dodging is telling me is that, let me just redraw this. This is the frequency. This is lambda q plus n bar. This is lambda q. And this is the geometric mean. Right? And WQ plus 1 essentially now has supports over here. Right? This is where WQ plus 1 lives. By this notation, I just mean that this is the highest frequency, so the thickness of the pipes, and this is the periodicity. Right. And what I'm claiming is that I can make, or what I want is that I can make these disjoint with all of these pipes. So any of these perturbations which has highest frequency larger than this. So in particular, there's something with highest frequency, say somewhere around here. Right? And this goes up to something around here, which was used to correct some error over here. Right? Somewhere like before in the iteration, I would have had to correct some error here. And the way I would have done that is I would have had to have a perturbation here, which has its highest frequency larger than lambda q, but still lower than this guy. Right? So this would have happened sometime before in the iteration. And now it seems a priori that these two guys can never have disjoint supports, because this here is the periodicity. of WQ plus 1. Whereas this here is the highest derivative cost, or also, in other words, the thickness of this previous guy, WQ prime, of this guy used to correct this, right? And so it's saying that the thickness of this is much larger. So let's say this is WQ prime, the support. So, and this is the thickness, which is lambda q prime inverse. Right? This lambda q prime inverse is much larger than the periodicity. So if WQ plus 1 was something which was, say, very intermittent, so very small, but its periodicity is going to be smaller than this guy, then there is no way that you will have that these will be disjoint. I mean, like this being disjoint with this implies that the periodicity is at least going to be this guy. And so you see here a very clear obstruction to why something like dodging should not be possible. And we'll need to get around this. So we'll need to modify our construction in such a way that it does become true that this will have disjoint support with this, whereas a priori this seems impossible. Yeah. All right. Okay, and I guess I have 10 minutes left. So let me. So this was. These were all problems that kind of arose because we wanted to bound this error term. Now, let me just very briefly talk about another error term and the difficulties that arise there. Yeah, we need to use some cutoffs and something else, but this is the topic of tomorrow. Okay. So let me talk about a different error term. Yeah. Yes, exactly. It's saying when I have some function which is supported on WQ plus 1, then I project it onto some frequencies. That projection is really the thing doing the smearing out of frequencies up to here. And so this is where I guess the term wavelet comes in our thing, because this thing will not actually be a Littlewood Paley frequency projector, because that would not preserve any spatial support. But what we actually need is some projection which both controls the space-time, I mean the spatial support, as well as controls the frequency, controls what the derivative cost of this will be. Yeah, this is in physical space. Yeah, all of this is in physical space. Yeah. And so here is where where this term wavelet in our paper comes from, because this will be a wavelet projection which will be able to control this. And we'll see that the smearing out, I mean, the uncertainty principle tells you it has to smear out at least to this much. And then this localized inverse divergence is going to tell you when you take the inverse divergence, you still preserve this. Yeah, okay. So let me talk about another error term briefly. And this is going to be the current transport error. Or, okay, actually, before that, let me just come back to the main cancellation, main quadratic cancellation. Okay. So, I mean, this is really the heart of the convex integration scheme for Euler, which I guess Camilo's already talked about, or will, and yeah, a lot of people have talked about this. So, which is the fact that if I want to construct a perturbation W such that WQ plus 1, and so WQ plus 1, if I take the low frequency part of this, which I mean is I have W tensor W, the Mikado tensor to Mikado, and I take the mean zero part of that. That will be the low frequency part of this. This cancels the error term. So this plus RQ is identically zero. So this is the type of, this is the algebraic cancellation at the heart of all of these Nash iterations. Okay. And the, and this puts some restrictions on what RQ can be. So for instance, this guy is always going to be a symmetric tensor. And so that means we need to impose that RQ is always symmetric. But this we can do. The inverse divergence lemmas that we have can always produce symmetric tensors. But something more important is this is always going to be positive semi-definite. And so if I want this to add up to the zero matrix, I better have that this guy is negative semi-definite. Otherwise, there's no way I can make this happen. But already this kind of seems unlikely because the error terms will be of this form. You'll have divergence inverse of something low frequency, high frequency, and up to leading order, I'm saying that that's some low frequency function, but then you have some divergence inverse of this guy. This guy, I mean, because, I mean, it's divergence inverse of something high frequency, it's going to remain high frequency, and it will not have a definite sign. I mean, this will be some matrix which will not be positive definite or negative definite, but will keep oscillating. And this kind of poses an issue because how are you going to get a cancellation when the new errors do not, do not have a sign as a quadratic form? And so the way one gets around this for Euler is one adds some function times the identity matrix in order to make this entire thing negative definite. And if you look at Euler, so let's say the relaxed form of Euler, I'm always free to add something like this. I can always add some function times the identity matrix here, provided I just change this guy to, instead of this, have nabla of PQ minus, is it 3 by Q? Right? Because divergence of this is just going to be gradient of this guy dotted with the identity matrix, which is just gradient of this guy. So there's no 3. So which will just be this. And so these two terms just cancel. Right? So I'm always free to, I always have this freedom that by changing the pressure, I can make this have a sign. I can make this negative definite. But this affects the current equation. So when you look at the current transport error, this was this error term that Hyunju wrote. You have dt plus uq dot nabla, uq hat actually, and then you have the trace of rq over 2, which was called kappa q, plus wq plus 1 square over 2. Right, and again, you'll have the same thing where this is greater than or equal to 0. And so if I want this guy to be high frequency or to have some, some possible cancellation between the low frequency part of this and this guy, I better have that this is negative. And so again, I will need to add some sort of the trace of pi q times the identity matrix here. All right. And this is something I will need to propagate. So the upshot of this is that at each step, when I construct an error, into the current equation, I need to add a term like dt plus uq dot grad of something, let me call it sigma q plus 1 q prime, so that the sigma is added in order to make what I called S here previously. This S, so this is an error, but to this I add a sigma q plus 1 q prime, which is just a scalar function, so that this times the identity minus this is going to be positive semi-definite. So I need to add this. And in the Euler-Reynolds system, in the relaxed one, I can do this for free just by modifying the pressure like this. So I can just add this and then change the pressure like this. And so that changes nothing. I can just do this for free. But in the local energy equation, in this, I will need to add a term like this. And so I will need to add and subtract this term in order to have it. And the part which I subtract, I want to put into divergence of phi, because that's the only thing which still has some freedom, which I can modify. So I'll have a new error term, which will go into phi q plus 1, part of, so let's say this is pressure, which will be like the inverse divergence of this guy. So this is a new sort of error term which appears because I need to add this in order to make this positive semi-definite. Okay, and now there is a problem. Previously, whenever we tried to estimate these guys, this was always something which had the form of a low frequency times a high frequency, right? For instance, like if it was, for instance, if it was the oscillation error, we had it of that form. For the transport and Nash errors, okay, I erased it now, but again, you had this form. You had a low frequency times a high frequency. And I mean, it's something high frequency cannot have a sign, right? I mean, if it has a sign, that means it has a mean which is non-zero. That means it has a zero Fourier coefficient. And this is something which has a sign, right? This is something which we have explicitly put in order to make that matrix positive definite. And so this has a sign. And so a priori, there is like no reason to believe that you can invert the divergence on this and get a good estimate. And yeah, trying to make this work, trying to find a way in order to add these guys in order for this to have a sign, gives rise to these errors, and figuring out how to deal with this will be the topic of Wednesday's lecture. So this is called the pressure increment that we need to add into our scheme here, just because we can't absorb it into any other term like this that was done in previous schemes. So I would say these are the two main difficulties of this work. Is that one way we need to figure out how to make this dodging work in a way, and it seems impossible. In some sense, like if I were just to follow this naive technique, it would not work. And the second main difficulty is this pressure increment. You need to add something which is like a pressure, but that in the local energy inequality gives rise to some problems. And estimating that, and trying to figure out how to get a good inverse divergence, and that will be what we'll do on the third lecture. And on Thursday's lecture, we'll go over some more technical details and odds and ends, and like try to see how to do the first step of the iteration, and try to see how I told you that this when we were measuring the time scale, we need to measure the L infinity norm of nabla UQ, but I replaced it with the L3 norm, like how to make that, how to justify that. So that I'll talk on Thursday. And yeah, so maybe I'll stop here and ask questions. That guy doesn't have mean zero, yeah. So you can't a priori even take divergence inverse. So you need to, like, first of all, take out the mean. But then if you take out the mean, then does that even have a good sign? A good, yeah, some good periodicity or something, yeah.
questions or comments?
Also, maybe, was this very fast or very slow? Or
Definitely not slow. But
okay.
it's
All right. I mean, yeah, I'm happy to discuss this. I mean, like, yeah, to go through the details of any of this with you guys. Just let me know.
okay, so let's go for the preview.